today's lecture. So we're gonna start the last topic. Okay, so chromatography. Okay, so now let's look into that. So today actually I'm gonna use a PowerPoint. Okay, so where's my PowerPoint? Okay, so because I have some animations in here, and then like I said, there's really no calculation, so then you please just look into it, and otherwise wherever I need to highlight, I will come back to my notes so that way I can I can highlight it with my pen. Okay, so now let's look into the last topic. Okay, so chapter 21 and 22, so it's about chromatography. Actually it has GC, gas chromatography, HPLC, but the HPLC most of the cases will emphasize on it. Another reason for that is because during the lab itself, we actually do this experiments with HPLC. Okay, so that's why I'm highlighting that way. Okay, so for chromatography, okay, so then it's another very useful instrument or technique. And then to separate, okay, so we can separate the mixture, okay, and of course from that point, actually we can get to type of information, will be quantitative analysis and then qualitative analysis. Okay, so we all understand, right? So quantitative is how much of a component is present, and in most of the cases in chemistry, we do calculate the concentrations. Okay, and then for the qualitative, you also will be identify what that is. Okay, so that of course, we think that's very powerful and useful instruments. Okay, so then you can get information like that. Okay? And as how we talk about in work, right? So like IR, right? So you can use that to study the functional groups, but then we'll say you will not be just use IR to identify what that is, right? So then that's just in terms of qualitative, right? So for chromatography, actually we could use instruments to identify what compound we have. It was the component in that mixture. Okay? So then that's quite useful, and then you can use it for whatever the purpose you have for the for using the instruments. Okay? And then chromatography itself is a process, like I mentioned earlier, to separate compounds from one another by passing mixture through a column that retains some compounds longer than the other. Okay, so basically there is an interaction. Okay, so there's interaction between your compound, your target, right, or your analyte, whatever you want to call it, the sample, right? So your interest, right? So all those things is describing your sample, right? So that has interaction with the stationary phase. Okay, and then in that mixture, right, you have more than one components, right? So they will interact with the stationary phase. The timing wise will be differently. Okay, so one will come out earlier, one will come later. Okay, so that's how we're going to separate the mixture. Okay, by the interaction, okay, between your compound and the stationary phase. Of course, we'll also have the mobile phase. Okay, so we'll talk about that. Okay, so and then as the terminology for chromatography. Okay, so we have mobile phase. Okay, so mobile phase, of course, from the wording mobile, right? So it's a solvent moving through the column. Okay, and then the mobile phase either will be liquid or gas, as I started off, right? So if it's a gas, you can also look at the third, right? So one, two, the fourth bullets, right? So if it's a gas chromatography, the mobile phase is a gas, right? That's quite straightforward. Okay, and if it's a liquid chromatography, the mobile phase will be liquid. Okay, and then the HPLC I have been mentioning that represents high performance liquid chromatography, so that the mobile phase will be a liquid. Okay, so that is just the mobile phase. Okay, stationary phase, okay, is either solid or liquid. Okay, so it's covalent bonded to a solid particles to inside wall of the hollow capillary column. Okay, so that stationary phase there, so that's what's also interacting with their sample. Okay, so that's and of course the word in stationary, right? So that doesn't move, and mobile phase, that's what's moving. Okay, so right, all the names are quite straightforward as well. Okay, and then we also have the fluid entering the column is called eluent. Okay, and then exiting the column is called eluate. Okay, so that's also that's related to where the interaction. Okay, so and then this process which is called elution. Okay, so I believe you don't see the very bottom portion, okay, but that's illusions also on your PowerPoint. Okay, so those are the terminologies. Okay, and then for chromatography itself, actually classify there depends on the interaction of your solute, which is your target. Okay, and with the extinction phase, you have different type of chromatographies. Okay, and of course in our course we didn't really go much into in depth about all this each each type of chromatography, but I just want to introduce to you there are different types of chromatography, and of course the working principles, then you can look into it. But in other words, I'm not going to test you on this, okay? So don't need to worry, okay? But if you later on you wanted to learn about it, right, that's there from our textbook, okay? So chromatography applications, okay? So of course, right, we learn all these instruments, we want to know when we can use it, what, and then when it's related to our daily life, that's what we're most interested in. Like, oh, I could use that instrument to do this, right? So, and then the first, right, many. Okay, so for this, we mentioned chromatography is that we can use this instrument to study, right, what's on the actual the bill, right? Okay, and then actually, some studies show there are drugs on the dollar bills, and then actually the study shows more than 80% of bills have cocaine on them. Okay, and then of course the other hint from us is, right, every time I believe we all talk to wash our hands after you touch the cash, right? Okay, so that just but then we can use chromatography to study about that. Okay, so that's one interesting application, right? So the other interesting application is normally in a regular class, I'll ask, well, how many of you like chocolates? But then, of course, it's okay. Okay, I don't know if you like chocolates. If you do, and then of course we also, right. If you like when you have it, you probably feel the right. You feel the right. You feel joyful after you eat it, and you have feel happy of that. And of course, we know that's not only one substance giving us that feeling or that reaction after you eat the chocolates. And then of course use chromatography, we can also study about the components inside the chocolates, okay? And then the other thing is, as I keep on mentioning, right, so of course chromatography is widely used in pharmaceutical companies, okay? So then also use quality control in terms of study the purity of the pills, right? As we also mentioned about, right? So the whole course is about precise and accurate, right? So when you have the products, right, we need to do quality control, right? So we need to see if our the pills are pure enough, and then you can use chromatography to study about that as well. Okay, so that's just some application. Of course, there's more than those three pictures. You can use it for all these different aspects. Okay, so and then as I mentioned, if you like those criminal shows, right? So then the normally I already mentioned this before, right? So if you see from the show, you have a huge box, right? So normally they put the evidence in there after several, right, whatever the time period, and they get the results back. Normally they meant that's a gas chromatography. Okay, so then you can study, like I said, you can even study low concentration of samples. Okay, we also mentioned that for, right, so when we talk about ASV, then you can study low concentration samples because you can concentrate the sample first and then you deposit it, right? So do the deposition and then stripping. Okay, so and then I hope you know why I keep repeating all these things. Okay, I hope you get the hints, and then if you have been paying attention, right, then it should be good for you. Okay, and then anyway, so that's for that. Okay, and then from yesterday, you also know you needed to know the difference between AES and AES and what it stands for, right? Okay, and then also those are already listed as the topics as well. Okay, and then for the separation, as we said, that's a separation technique, right? So you have a mixture, and then depends on what your target is, and then of course you can choose either use gas chromatography or a liquid chromatography. Okay, so it depends on what you have, right? So and of course if you wanted to study compounds on the left bottom corner, then you're probably gonna choose gas chromatography, and then otherwise you'll probably need to choose liquid chromatography. Again, depends on what kind of sample you have, right? So think about it, gas chromatography, right? For the sample itself, you actually need to turn your sample into gas phase first, okay? And then of course, then we all know by the chemistry concepts we learn, right? So the compound cannot be a very huge molecule, right? If it has a huge molecular weight, it's going to be very hard to turn into gas phase. Okay, so then therefore, if you wanted to study or if you wanted to see if your sample is applicable for gas chromatography, then you should think about if the molar mass is not that huge, right? If it's that huge, such as amino acid, if you see on the top again, sorry, I cannot highlight on it, or for a completed compound, if it has high molecular weight, then probably not easy going to be turned into gas phase. Okay, so that's just something about that. Okay, so gas chromatography. Okay, so as I said, this whole topics including both. We're going to talk about both. GC, which is gas chromatography, HPLC is high performance liquid chromatography. Okay, and of course, it's only limited to these two. Also, I don't know if you have used, you probably did TLC, thin layer chromatography. Okay, so that's also a chromatography working principle. The major working principle is the same, right? You use right, so the thin layer, right? So that silica gel, that's what you have, right? So that's the stationary phase. Okay, and then you also use that to separate your samples. Okay, so the working principle is similar. Okay, so anyway, back over here, the GC we're focusing from this course, which is gas chromatography. You can separate and analyze compound. Okay, and of course, as I said, the sample itself, it should be relatively easier to be vaporized, right, turn into gas phase without decomposition, which means, right, so if you go, oh, my sample, right, I turn into gas phase, right, and then it's going to decompose into something else, and that's not good, right? So you're not really analyzing or focusing on your sample anymore. It's already turning into some other compounds. Okay, so that's also something we need to pay attention. Okay, and this is just showing you the box I was mentioning in those shows, right? So then you see a box, and now of course the core is actually the column is on the bottom right corner. You see that that's after you open that box, right? That's where you see the core is the column. That's where the sample passing through. Okay, and then there are different types of column as well. And then also for GC, normally it's inside. Actually, you have an oven, right? So you can do temperature control, and then depends on what kind of sample you have, you can do different temperature program to adjust and to develop method to separate your sample. As I said, right, so some people actually have their whole career based on chromatography, either right, could be GC or HPLC. And then actually, when I just I work for a small company. They were working on GC, and then actually working on portable GC. So they are developing a GC instrument. So then it's actually is the intention is to develop that, and then right, we can detect disease, right? So basically, you blow into the GC, and then will be able to upload the data onto central, right, the data treatment, and then we'll see, okay, if someone has right, certain disease. Okay, so that's some project I worked on, I think, which is quite interesting and useful, right? So anyway, so that's GC, but of course this is not portable, right? So it's a huge one. Okay, and then actually in our department we also have GC, and then in the analytical lab as well, we actually did a demo for the experiment as well. Okay, so how GC works. Okay, so and then you can inject your sample, and then there are different type of samples. Maybe originally you have a gas phase sample already, and if you see on the left, right, so that bag looking, right, so that's you can just, if you have a gas already, then your gas is there, then you can just you can have that hook up to the instrument, then you can just have the sample injected that way. Okay, or you may have a liquid sample, but which is easy to turn into gas phase. Okay, so then you can just inject it into the instruments. And then, like I said, the column is really important. You have capillary column and packed column, depends on what sample you have and where your target is. You're going to choose the appropriate column as well. Okay, and then we also, the other important part is the detector. There are more than 20 different types of detectors for chromatography, and then there are several commonly used ones, at least over here for GC, TCL, thermal conductivity detector, FID, flame ionization detector, ECD, and MS. And then again, MS is also very, very powerful when it's connected or is combined with GC. Then that way, right, you can actually at right mass, right? You probably learned this from Oracle, or you heard of this before, right? So you can actually identify what that is by learning, right? So by learning by doing the separation, you also can actually figure out what the mass is for that particular sample. Okay, so then when you have GCMS, it's a very, very powerful instrument. Okay, so just for this, and this is just showing you the one of the what is it, the detector, flame FID, flame ionization detector. And here's showing how this works. And then again, since, right, so I'm not gonna go too much into details about it. Okay, so the other thing is, right, so when you have the detector, Oh, right. Okay, so it's right because it was moving earlier. Okay, so right over here. Okay, so for the detector, right? So depends on where your sample is, where your target is, and you're gonna choose the appropriate detector. Okay, so then of course as FID, right? So it's good for analyze organic compounds. Okay, so that's what it's good for. And then actually for the Orgo lab, I taught before at a different university, we actually use GC and then with the detector as FID. And then we were, that's a Orgo lab, we synthesize and we use GC to analyze our sample. And of course, FID is a good choice because it's good for all organic compounds. Okay, and it has little or no response to the following gases list over here. Okay, so that's just for all that. Okay, and then for advantage for GC requires very small sample. Like I said, that's very good because sometimes you don't have that much sample, right? Okay, so if only it requires a little bit and with little preparation, that's awesome, right? So that's what we want, right? And no matter what we do on convenience, right? Okay, and then good at separating complex samples into components, and then results are very rapidly obtained. Because normally this is also important for you to notice, right? So normally, right, so later I'm gonna show you the chromatography how they look like, okay? And then normally the x-axis is in minutes, okay? So then basically you're gonna run the separation, and then you're gonna get separation within, we'll say, right, between right 2 to 10 or 15 each minutes will be good, reasonable. Okay, so otherwise if you have a separation, you have to sit there wait for hours, right? So that's not good, and we need to adjust our parameters to make sure the separation happens a little faster, right? So we don't want to sit there for hours just to wait, right, for one result. Okay, so then that's just again as another as advantage of GC is that you do get result quite rapidly. Like I said, the experiments we design for the lab, actually you get the separation. We actually like work on it and make sure everything works out before you guys actually do the experiments, and then we make sure the results comes out around within 5-6 minutes. So then right, the groups wise you can all take your turns and then do the separation. Okay, and then for GC you also get very high precisions and only instruments with the sensitivity to detect volatile organic mixtures of low concentrations. Equipment is not very complex, but uh, sophisticated oven. Like I said, the oven is the core, right? That's the heart of the instruments. And then that's a part definitely we need to take care for if you get to have hands-on experience for GC. Okay, so that's for that. And then the other big instruments, right, or the another type we want to talk about for chromatography is HPLC, high performance liquid chromatography. As I said, right, so from previous semesters, right? So because that's in person, of course, right, people getting very creative about HPLC. They get all sorts of right um, the for this abbreviations. But I hope you know it and you don't have to search for it during the exam because that will be just wasting your time, right? So let's just focus here real quick. HPLC is high performance liquid chromatography. Okay, so that's what it represents for. Okay. And then from this portion, definitely I have some questions on this conceptual questions testing on your final. I hope you're following, and then you don't need to search for it tomorrow. You already know the answer. Okay, so that's hopefully we can get to that point. Okay, so then we're gonna talk about chromatography from this aspect. Okay, so the first one will be principle. Actually, before we go, I have a cute short video for chromatography, and I hope also that helps you to understand again the whole let me just re-share my screen so you can see the you can hear the audio. Okay, so now let's do this again. Okay, and then again, hopefully you understand you have a mixture, then this technique, this chromatography, right, is separating the sample into the individual components. Okay, so that's, see. Okay, so here we go. Okay, hopefully today you can hear the sound. Okay, here we go. I hope you enjoyed the video real quick. But anyway, so that's right. So as an animation, just showing you had a mixture, then you have your stationary phase, you have mobile phase. Mobile phase doesn't matter it's gas phase or liquid phase, right? That or it's a liquid, bring your sample along the column, and then during on the right, the column is where you have the stationary phase and interaction happens, and then depends on the properties, right? So between your sample and the stationary phase, and then have different interactions, and then they will get separated. Okay, so that's just how that works. Okay, so now let's look into the principle for chromatography. Okay, so for high performance liquid chromatography, and then we actually going to use high pressure. Okay, so yes, it is. We're going to use high pressure, but then actually it represents high performance, not high pressure. Not pressure. And so high pressure to force eluent through a closed column packed with micrometer-sized particles that provides exquisite separations. Okay, so again, because the column itself, right, it's very it's the size is small, okay? And then if you wanted to push your sample through, think about it. We need to use the high pressure to push it. Okay, so then there's also another. Oh, let me re-share so then it doesn't show you the tiny screen. Okay, so let me just. Okay, now it's all good. Okay, so then again, you will need to apply the high pressure, and of course, pressure will be one parameter you need to look into if when you actually use the HPLC. Okay, so then actually when we use HPLC, you turn the instrument on, you turn the detector on, you actually need to wait depends on 10 to 30 minutes to make sure the pressure gets stable. Okay, so that's also one of the things, of course, from principle that we know and how to operate during the actual settings. Okay, so anyway, so you can use high pressure, and then you get, if you look at the bottom spectrum, that I mean, this is a chromatogram. Okay, so then this is gonna how it looks like. So you're gonna have different peaks depends on how many samples you have. Okay, so then you can separate them. Okay, so that's just roughly how it's gonna work. And now, of course, there are several important terms that we need to pay attention to. Okay, so this is one of the term you need to pay attention. Right? Hint, hint. Pay attention. Okay, so this is something we need to no, okay. So theoretical plate numbers. Okay, so this is chromatography column as you were divided into discrete sections. Okay, so that those are called theoretical plates. Okay, so then basically your sample and your molecules are will be having equilibriums. Okay, so basically it's gonna go interact with the station race and then go to the mobile phase, and this multiple times. Okay, so then get separated. Okay, so that's what we call as number of plates on the column. Okay, so of course there is an equation to calculate, but remember, I said there will be no calculations based on that. But the one thing you need to know is, in theory, what we're looking for, what's gonna give us good separation. Because of course, that's what at the end of the day we'll use these instruments. That's what we want. We want to get good separation. And then we need to know what's giving us good separation, right? So the more the theoretical plate numbers, the narrower the bandwidth, and then it's getting our the better separation. I'm sorry for the bottom line, you don't see it, but then that's also on the PowerPoint. So, but just hear me out, right? So what do we want in terms of the theoretical place number? We want more, okay? The more, so basically the more time, the more equilibrium you have between your solute and between the mobile and stationary phase, and that's better. That's how we can get better separations. That also makes sense logically, right? Okay, so then one more time, okay. I hope you don't need to waste your time searching for this tomorrow, okay. And I'd say one more time, okay. So the more you're looking for, or larger, or whatever the word, right? So as how the question is lasting, but meaning the same, right? So the more of the theoretical place number, that's what's good for getting a good separation. Okay, so that's just for them. Okay, and of course, all these equations, right, you can do calculations, and then all the actually some values you can get from the instruments. So right, we all know the instruments are very advanced now, right? So giving us all this most number we need is given, but then from us, right? So like I said, the next step is we need to know how to use those values to do analysis or interpret the results. Okay, so that's just for that. And then the other term you need to know is a plate height. Okay, so plate height is defined as, right? So H is the length of the column divided by the number of theoretical plates. Okay, so now think about it. We were just saying, right, that number, the N. Okay, so we want the large, we want more of theoretical plates, and then the length of the column, right? If you already know which instruments you use, the length is certain, right? So the column, right? That's the physical, this column. Whatever the length is certain. Okay, so like I said, the one we use a packed column for HPLC, and then that's about this length. Depends on what you use. Okay, so that length is certain. Okay, so if we want a good separation, we already know the N value needs to be large. Then accordingly, based on this equation, we'll know the height, right? So the plate height, we need it to be small, right? Just very easy relationship, right? So then again, to get a good separation, now we know, right? We want more the theoretical place number, and then we want small plate height. That's what we get, how we can get good separation. Okay, so two things, right? So there's more, but I hope you already get this too. One more time, the height, the plate height we want small, okay, and then the number of theoretical plates we want large, we want more. Okay, so that's what we want to get good separation. Okay, so that's for that. And then resolution. Resolution is the neighboring peaks, the peak separation divided by the average peak width measured at the base. So basically, right, you get a separation, right, for the sample, right? So we want the resolution to be good, right? Resolution will also sort of use it, right, for like pictures or the qualities, right? So then resolution, you want the two peaks to be separated, right? So and then that value itself, normally, if the resolution is bigger or equal to 2, then we say that's a good resolution, good separation. Okay, and then if they're overlapping, I just say, oh, you see two peaks, but they're overlapping, and then that's not good. When later I'm gonna use my notes so that I can draw, and then you see what I'm saying. Okay, so then that's just for that. Okay, so that's the resolution, another term. Okay, so we also have a term which is called eluent and eluent strength. Okay, so eluent, I already talked about it. So the fluid, if you also can see the image on the PowerPoint, a fluid entering the column is called eluent, and the fluid exiting as eluent. Okay, so that's also the mobile phase, right? The solvent we use. Okay, and then also that also has interaction with your stationary phase, and then we want to, again, that also matters at the end of the day, what kind of separation we can get. If we can get a good separation, and also another way, in another, from another perspective, if you getting a rapid separation in terms of, well, is this going to take forever to separate my sample, or I can adjust the polarities of my solvent and then get my separation, good separation, also get them out relatively fast enough. Okay, so that's also another parameter you can play or you can design with when you design experiments. Okay, so then there are several solvents are here listed, and then it has their eluent strength and and then again, we have to notice the other thing is for HPLC, we actually have two different types of HPLC we're talking about. Okay, so it depends on which type you're mentioning, but the two highlighted ones is the ones we use in the lab. The solvents we use actually is for the old lab, and then actually for the spring, we actually designed a new experiments on HPLC, but unfortunately, right, so after March, right, everything's closed and we didn't really get to do this, but I actually did it multiple times. I made everything works, but then the student didn't actually get to work on this. Okay, and then but anyway, so hopefully if you're gonna take the lab next spring, hopefully everything will go back to normal, then you'll get to do the experiments. Okay, and then again, the working principle, as I mentioned, is the solid molecules compete with the solute molecules, the interaction with the stationary phase. Okay, so then we'll see, then depends on the interactions, and then we try to come out faster. Okay, so that's just for as a major working principle, right? So that's for that. And here, as we said, you get qualitative analysis. So then normally, right? So normally you have sort of idea what's in your sample, okay? And then you also have a reference, okay? So again, under the same condition, right? From the reference, you probably know, okay, if I have a benzyl alcohol, just saying, okay, so it should come out around 2.3 minutes. Okay, and then you run your sample. Okay, so you also have a peak at that time. Okay, so at the retention time, you go, oh, then I probably have a benzyl alcohol. Okay, and then you go, I want to be certain. And now another way is do spiking. Right, that's also something we learned earlier. And so we can use the same, right? Use the same sample. I use a pure right, manufactured pure benzyl alcohol, I'm gonna inject as well. If we see if shows up to 2.3 minutes, if so, you go, okay, I'm certain that my sample has benzyl alcohol because I did a spiking, right? My peak at that time, at that retention time increased, okay, because right, that's matching the benzyl alcohol. Okay, so that is a qualitative analysis. Okay, so like I said, if you have an unknown, okay, and then when you spike it, right, so like the the signal increase because you added the manufactured or the pure A, and then it did increase the signal. Okay, so that means the concentration increased. Okay, so that's this. I think that's my. I don't know if you're following. I hope you also feel good about this because we talked about stacking before from the beginning of this summer, and now again this is, and we also have something else we mentioned before, and then it's gonna come back again. Okay, so that's just for that. And then for quantitative, right over here, right? So we're gonna use internal standard method because, right? So like we said, there is the problem with reproducibility, and the internal standard is a good way to help with that, to solve that problem. Oh my gosh, sometimes I'm scared. Uh, yeah. I didn't expect that. I'm sorry. Okay. Yes, I was saying, yeah, so you can use internal standard to help with that problem. And then, like I said, for right, when for the big pharmaceutical companies, right? So they probably have the instruments with auto sampler. So that's probably will be better, right? So then that will reduce the reproducible problem. Okay. And then in terms of in our lab setting, right? So we definitely will have that issue because right, even me, the same person do the injection every single time, there's still error happens, right? Okay, so therefore we will actually in this lab we design internal standard method to carry out these experiments. Okay, so and then also we use internal standard to resolve that problem, which is the reproducibility problem. Okay, so that's for that. And then the second portion is HPLC, the instrumentation portion. Okay, so this is the instruments we use in the lab setting. The other thing is, right, so again, I don't know if you are just say, maybe you're interested in analytical, right? So you want to be analytical chemist and you want to work for a big pharmaceutical company, and right, so then when you, the other thing is actually me myself, right, I had experience, right? So when I went for interviews with a pharmaceutical company before, right? So they they did they literally actually when I went anyway, so they literally asked, right, which instruments I use, what's the model, and what's the software you use. That's why when if right you think this is something you're gonna put on your resume, so make sure you know the answer for these questions they really did ask. Okay, so then if you have the answer for it, okay, which we should, right? So then that's awesome. They go, oh, they did have experience and they can talk about it. That's a big plus for you, right? So if you're on, right, you're looking for a job like that. Okay, so then this is the instruments we have. Actually, this is discontinued, and I think this company is about Agilent, which is a huge instrumentation company. Okay, but then this is the model we had, and then the software we use is called Galaxy. Okay, so then that's just just the instruments we had. Okay, and then of course you have other fancy versions, and then like I said, you see this is right. So you have to normally have two pumps, and you have detectors, and then like I said, if it's a more modern one, right? So you have the auto sampler. Okay, so that's just all that. Okay, and then this is again one more time. This is exactly what we have in the lab setting. I took the picture from our lab. Okay, and then you will have the two pumps. Okay, we'll have pump A and pump B. And on the top is the UV detector. That's the detector we use. And then you have this injection port. And on the right side, that's the column I was mentioning earlier. So that's about this, the length. Okay, so you have the column. Okay, so as I said, the column is where the separation happens, right? Okay, and then you also have this is the diagram for the instruments, and then you can look into it. Okay, so then we also have the injector. The injector is also quite important. Okay, so then there is a small animation. Okay, so then if you inject, you please pay attention to the red dot. Okay, so you inject the sample. Okay, so then it's gonna onto the sample loop. Okay, and then you're gonna the other one, right, solvent in is gonna carry out, and then to the column. Okay, so that's how the injector works. Okay, so of course, when actually if you're taking the lab, we'll talk about more into this as well. Okay, and then so you have this. That's the 6-port. That's the from the animation I did. That's the 6-port injector. Because that's how that happens when you load your sample and inject and load your sample. Okay, so that's just how that works. Okay, so then like I said, injection, normally we use very small quantity of the sample, which also very good, right? So because right normally we don't have a lot of sample available, maybe not. Okay, so then you can you only take microliters to do the injection. You can still get the information about it. Okay, so just for that, and then for column itself, as we said, the column is the core, of course, right? Economically, it's very expensive as well. Okay, so then that's also we need to know what we're doing, not just inject whatever into the instrument, and then that will actually damage the column itself. And then, but for the design, so there are actually two types of the column. I mean, on the column, there are two parts. One is the analytical column, where it's actually the separation happens, and then that's expensive. Normally it's, the cheap ones or the like no brand is at like $200-$300, and if you get the good brands, then it goes up like $700-$800 for one piece for the one column. Okay, so and then for the column itself, there's normally a guard column, which is short, expendable. So which means, right, if you had some samples that you didn't really know or you want to study about the unknown sample, right? So then the guard column is actually going to catch whatever is not good for the column. And then if you ruin that, and then we can change it. We can change the guard column. But still, again, before we run, actually, we should study enough or design our experiment well enough and then use the instruments. Okay, so the column, it is quite extensive. Okay, and then the separation, as I said. Okay, so for the separation, the particle size, right? So the relationship is that if you, I want to quickly talk about it, right? If you look at it, right, so the number wise, again, one more time, we wanted a large number, right, to get good separations. And then if you see these two separations and accordingly, right, so the bottom one apparently is a better separation. And then in terms of the particle size for the stationary phase, if it's smaller, also give us a better separation. But of course, there are other parameters we need to think about. There's also an equation to describe the relationship between all this. Okay, so we're not getting into that. Don't worry about, like I said, equation wise, don't worry about in this course, or at least for our, I know I'm not gonna bother you about this. But then, like I said, if you're interested in this technique, right, it's very, very useful and might get you good jobs, right? Okay, so anyway, so and then for stationary phase, there are different stationary phase, and then here I showed you some, and then actually these are the SEM images as I, right, myself, I also have some experience with SES image. You can study the morphology, you can study what the particle size, and then that's also a huge instrument, and then it's good to know about. Okay, and then in our department, we also have ICM, we have AFM, we have several quite expensive instruments from our department. Okay? And then back to mobile phase, you have the southern system, you have detector. As I said, for our HPLC, we're using UV, and there are other detectors as well. As I mentioned, if you combine the with MS, right? So mass spectrometer, right? So that's also very, very powerful because it also will be able to study the mass of your sample. Okay, so that's for that. And then the next portion is the types of HPLC. I'll quickly go over. And so it's normal phase chromatography, reverse phase chromatography, and ion chromatography. Okay, so the one you need to focus. Okay, important. Okay, important. If you're not paying attention earlier, please pay attention over here. The reverse phase chromatography, okay, so it's commonly used, okay, so it's more common, in which the stationary phase is a non-polar or weakly polar, and the solvent is more polar, okay, and then this is more applicable or more common because then it's better at separating polar it will be more applicable for more samples. Okay, so again, reversed phase chromatography. I say it one more time. Okay, so that's what's important. Non-polar stationary phase, non-polar stationary phase. Okay, I hope you don't need to look for this tomorrow. Okay, so I made it. There cannot be more obvious than this, but please pay attention. Reverse phase chromatography, non-polar stationary phase. Okay, so non-polar stationary phase. Okay, and then the other way around, if you have normal phase, that'll be having the polar stationary phase. Okay, and then in general, Elohim strength is increased by making the mobile phase more like the stationary phase. Okay, so that's just when you try to play around or design the method for your separation, and then that's all these things you need to take into consideration, right? I highlighted one more time, reverse phase chromatography, and there's also this RP chromatography is what we use in the lab as well. Okay, so it's reverse phase, non-polar stationary phase. Okay, so less polar solvent has higher eluent strength. Okay, so and of course you have different materials and all this chemistry behind it. I'll leave it alone for now, but if you're interested, you can look into it. And then actually we're using the carbon 18 stationary phase. Okay, so I'm laughing because we had pre-lab quiz and then the TA came up quite interesting options for that question. But anyway, so if you're not taking the lab, it's fine. I'm not doing that for the final, but one more time, reverse phase chromatography. We're using C18 non-polar stationary phase. Okay, so as I keep on readdressing on it, right? So it's a non-polar stationary phase for the reverse phase chromatography. Okay, so that's for that. And then for right, so now we know the stationary phase is nonpolar. Okay, so then if you have the stationary phase is nonpolar, such as my picture drawing, so it's C18. Okay, and then now think about it, right? So now it's serious, right? So think about this, right? So if you have a sample, okay, so the interaction I keep talking about, right? So apparently, right, so it's related to polarity, and then this is also something we learned already, right? So if you have, right, what kind of interaction is going to be strong, right? So we said like dissolves like, right? So that's the thumb rule of chemistry, right? So then what is it? So if you have similar polarity, they're going to have a stronger interaction. Okay, so now let's look at my reverse phase HPLC. My stationary phase is non-polar. Okay, so and then I have all this, right? The red will be very polar, and then the blue will be moderately polar, and then the green one will be non-polar. Okay, so then now think about it. Which one is gonna come out first? Okay, so that's something we need to be able to identify. Okay, so I say one more time. Okay, so you have the non-polar stationary phase, and then the working principle is how when they're gonna have stronger interactions, they have the similar properties. Okay, so if I had similar property, they have stronger interaction, they're gonna stay on the column longer. Okay, the one right doesn't have similar, the green one right is gonna stay longer. Thank you so much. Now I know someone is following me. I'm really happy to know that. Thank you so much. Okay, so then now that's, hope the animation works. Okay, right, so the red one will come out first, and then blue one will come second, and the green one, right? Thank you, Sadia. Right, so the green one is gonna stay behind. The reason for that because our column itself is non-polar, and then the green one itself, right? The molecules are nonpolar, so they have stronger interaction, so stays longer. Okay, so that's how this works. Okay, and then in terms of if you had the chromatogram, right? So think about it, right? So there is time, right? So the red one, right, is A, is polar. Okay, so it doesn't have similar polarities with the stationary phase, so it's gonna come out first. That's why you see the first peak, right, is showing you that's the most a polar molecule. Okay, so and then accordingly, C, which was the green one, is gonna come out later in terms of retention time wise. Right? So it's gonna take longer time for it to come out. Okay, so this is how the working principles for this. Okay, so that's just for that. And then I just have as comparison if I have polar stationary phase and non-polar stationary phase. And if you're interested, you can look into all this. Okay, and then the next portion will be method development, as I mentioned. Right, so actually, this people are having their whole careers on this, and there's a lot to learn or a lot to design about this, and then it depends on what kind of sample you have, or like I said, the first thing you have to think about what kind of molecular mass you have, then you're gonna go for the proper method to do the separation. Okay, so again, I'm not asking you to look into this, but this is just something I want to bring, right? So there is a thing, right? There's a thing about chromatography, and then if you're interested, right? So that's something right, you can like pursue as your career, I think that's quite interesting as well, right? So you can study or develop a different method to separating, right? So like, right, whatever the drugs, right? If you're working for a pharmaceutical company, and then, right, so what method you is applicable for a certain drug or all this, right? So do separations, okay? And then for the method itself, right? So you have to choose the stationary phase, and then depends on, right? So you have to choose stationary phase and you choose mobile phase, and then all these, and then sometimes we'll also have additive types. And actually, one of the undergraduate days we did the whole research or study on this and trying to develop the new lab for our lab, and also we're trying to work on a paper to study all about this. And then we actually tried with changing the pH of the solvent by adding some additive to our solvent system, and that's, again, that's part of method development. Okay, so anyway, so that's for that. And then the other thing is, right, so again, if you're designing, right, so we have to know what's the easy fix, right? What's cost less, right? So if you change the solvent strength, that's easy, right? So you can just change the ratio, right? So the solvent sometimes is one, sometimes it's mixture, depends on what kind of polarity you want for your separation for your method. Okay, so that's one thing easy, right? So you can just adjust the ratios between your solvents. Okay, and then you can also change the temperature. That's easy because you can adjust if your HPLC advanced enough. You may also have the oven. Okay, so then you can change the temperature, and also the pH, as I mentioned. You can do the additives to the solvent system and to change the pH, and you can use different solvent. And then of course the harder to change is that the stationary phase, the column itself, right? So because it's expensive, or right, so when we trying to develop method, we don't want that's our first choice. Oh, we're gonna change it mobile. I'm sorry, we're gonna change the station for. One's just gonna buy a brand new column, right? That will be the last thing you want it to change, right? We're gonna try to adjust other parameters, which the easy ones first, right? Okay, so that's just for that. And then for you also have, right, the triangle, like I said, the solvent. You can try out and see what's most appropriate for your method, for your separation. Okay, and then we also have the typical solvents for HPLC. You have THF, you have water, methanol, acetyl nitrite. Actually, for our method for the lab, we use acetyl nitrite and water. We use different ratios. We study different ratios and see how that's affected the separation. Okay, so that's for that. And then we also have the isochromatic elution. So basically you will have at a constant solvent mixture. Just say I'm using 60-40 between my isonitrate and water. Okay, and then I want to see how the separation is. And then sometimes you're going to use gradient elution. So basically you're going to say my mixture, the ratio between my solvent, which is my mobile phase, right? So it's going to change throughout my separation. Okay, so the other reason sometimes we use gradient elution is that, as I mentioned earlier, right? So when you separate the mixture, maybe your first two targets are already coming out around 2 to 3 minutes, but your last one, it's gonna take forever. Where, right, it has very similar polarities with their station phase. It's gonna take forever to come out. Okay, and we don't want that. We don't want to sit there waiting for hours just for the last compound to come out, right? So then we can adjust the polarity of the solvent and then make the last peak come out earlier. Okay, so that's also something you can play around and then try to get the best method, right? So that's part of method development, and then to get a good separation. Because as I say, if you see all these ones, if you see the last peak on the very bottom, okay, so if you see I have a peak 8, right, it's come out at 120-25 minutes, okay, so that's taking forever. That's 2 hours, okay, you have to sit there. On the other hand, the other peaks are already coming out 5 minutes 15, and then you have to wait the last one for 2 hours. That's not good, right? So what are we gonna do? You can use a gradient illusion. So you're changing the ratios between your solvents. So make sure the last peak comes out earlier. Okay, so after you apply this gradient illusion, then you see peak 8 come out around, right? So around what, 30 something minutes. So that's reasonable, right? So that's just something, definitely, if you are planning, right? So if there's something maybe later on you will use, and then that's something we definitely need to keep in mind. Again, if you're taking a lab, we'll actually use this as well. The whole experiment design, you will also do gradient illusion, and you see how this affect your separation. Okay, so that's just for that. And then the method was now after you do the separation, right, you get your data, and then we actually we use internal standard. Actually, we had an internal standard, and then we'll be able to study about the sample, and then again use this to right to counteract that problem with the reproducibility. Okay, so and this is something you're familiar with, right? So this is the equation you use for internal standard and then do the calculations. Like I said, the whole experiment actually applies all these things we talk about in the lecture, and then we actually use all this in the lab as well, and then use this right all these principles, and then you know in the lab setting. Okay, so that's it for the lecture part. Okay, so